my pleasure to join this COCO event again. This time in the US, it just moved, but it's still based on these two works with this awesome collaboration back in Hong Kong, U Science Tech. So today, the topic would be very simple. So what if our cosmology change if Higgs VEV, a very familiar constant, is no longer constant, the changing, it's a changing field, and how possibly it solves the problem here and there, and what if we go to an axionic solution and deal with everything. So the motivation is very simple. So we noticed that there are several discrepancies, or like say evidences that the lambda CDM is kind of under siege, or is less satisfactory. So this is the well-known Hubble tension, the late time measurement, and the extrapolation from Planck and lambda CDM disagree about like 5 sigma-ish. On the other hand, it's a long-standing problem in big bang nuclear physics. That's the so-called lithium problem, that your theoretical prediction of a lithium-7 abundance is way larger than the observed value by a factor of 3. And this is way beyond nuclear physical uncertainties, which must be explained. You already know from the talk this morning very well, this is like less updated, but I think it's roughly the same spirit, that the so-called sigma-8 or SA tension. It is a tension, I would say. I agree that they can cope with each other, but in some cases it can be worse, which would be like say 2 sigma-ish difference. At last, we also noticed the recent reanalysis of CMB data find out a parity violating or PR component of the CMB, which deviate from 0 like by 2.4 sigma, that indicates a isotropic cosmic bifringent effect, or simply ICB. So in the plot, they look like, okay, this is Hubble tension, all the late time measurement, and this is the early one from Planck. The lithium problem, okay, so this is like, we know very well the barrier to photon ratio, there's no way we can change. And this is theoretical prediction, small uncertainties, and this is what you see this plot like multiple times today, so just skip this. And also the 2 different curves right here, as long as they're different, indicates that the ICB is not 0. So let's go to the lightning review of the idea, like how a changing VEV is going to say today, and what if, like, what the axion is going in our model. So we first noticed that the Hubble tension can be greatly alleviated already if the electron mass, here we change the electron mass by, like I say, increasing the VEV. If the electron mass is long constant, but it's not, I mean, it's depending on the Higgs VEV. So as long as 1% heavier during and before the recombination, say, when the redshift is like 1100. So this shrinks the Bohr radius. We know from the elementary quantum mechanics. And because the cross-section is basically a disk, right, described by the Bohr radius by some ratio. So this decreased interaction rate, the smaller cross-section, gives you an earlier freeze-out, or earlier finishing recombination. This gives you the early freeze-out recipe of the Hubble tension. I will mention details later. But beyond this, we notice, well, the VEV not only changes the electron mass, it changes almost everything, including the quark masses. And this brings you nuclear physics, new nuclear physics, that if we trace back to BBN, well, assuming the Higgs VEV is also larger than by order percent than the current nowadays value, the increasing quark mass gonna solve you the lithium problem, and it's still compatible with data. Beyond this, let's describe or just mention why we go to the axionic solution. So you can imagine the Higgs VEV can be changing due to several reasons, but one of the easy ways to demand a slowly changing field that moves the Higgs VEV. Because we need a time scale right around recombination, which is for the million years, this can be easily done by just put the axion mass by hand, just the mass scale. This very light scalar therefore suppresses the structure formation below a certain threshold. Therefore, it naturally gives a solution to the sigma 8 tension. And also, it's very easily you just the nature of the axion, the AFF tilt coupling, which is the parity odd coupling, is going to give you a non-zero ICD piece of cake. So let's explain what happens when we observe CMB. So the most sensitivity of the Hubble coming from CMB is determined by simply measuring the sound horizon as an angular scale with theta star here, described by the sound horizon R star and the distance of the last scanning surface from us. So the early recognition as the solution leads to a higher Hubble as such that without freezing the remaining parameters. Okay, let's do this first. And then we just, because introducing the alternative recombination history, this is not standard model, right? So we need to calculate again. And the Z star, because it's earlier, so Z star is getting larger. So less time to develop a sound horizon, therefore it shrinks. You can see that the dependence is negative and is significant. On the other hand, the D star, the distance, it's dominated by the late time expansion. So it hardly feels anything like at the very beginning. So you can see almost no response. So if we just introduce a larger electron mass, this shrinks, right? I mean, we only reduce R star. So the simplest way to say this is to introduce a larger cosmological constant, or the other terms you can imagine here. So this leads to a higher Hubble, and then as a compensation, both decreases, and we can still have the same theta star. So in the more realistic approach, we need to introduce the CMB. You can see it's indeed very precise, and also the BAO measurement, say the RDH, roughly speaking, yes. And in the RDH plane, we can just plot different constraints, and this is the late time measurement by Hughes, for instance. So we employ this model by introducing a higher Higgs VEV. Of course, right now, a priori, we have no idea how big it is. It's still a free parameter. So it depends on how much how big the VEV increase you allow. By putting 4% increase from nowadays, you can raise Hubble, the central value, up to 71. If it's just 1%, then it's 69, still better than the current, say 67 values. During the process, other parameters also change, especially the cold dark matter fraction, or say the matter, in order to cope with the data. This is important. We will go back to this point later. So it's now time to introduce Axion, which is every day. People talk about this more and more. Of course, this is indeed not really an axion, but an ALP axion-like particle, but let's call it axion for simplicity. The term itself is decaying. So let's just write down, because this is Higgs VEV. So what if an axion plays the modulator rule of changing VEV? So we start with the standard model, just like this, very funny shape, and this notorious hierarchy problem tells you you have no idea where this term comes from. So it is equally legit, let's say, to address this term, okay, including this one, with these axionic terms. You can imagine this is the first expansion of a cosine type of typical axion behavior. So these constants of order 1 without further theoretical input, they may just come up from string theory, for instance, and without also further input, the scale that's downstairs, we can put we simply choose Planck scale right here, and it turns out worked pretty well for us. In a more formal way, you can just imagine this can stem from these are all cosine terms of axions. Such a supersymmetric theory is going to give you such a behavior. So without fine-tuning, say, without conspiracy between these constants, once this axion field starting to roll, changes, and this A squared over M Planck squared changes by order 1%, then the Higgs VEV also changed by order 1%. And that's enough. That's what we need. So now we can just turn to the misalignment mechanism that we know that Hubble friction is going to keep the axion field at the plateau, or say freeze at the a metastable position, and then after a while, say Hubble decrease and start to oscillate. And then nowadays, the Higgs VEV change induced from the oscillation is so small that it's hard to detect and it's still allowed nowadays. And during the process, Higgs is always sitting on the bottom because it's, well, I mean, the decay width is like 4 MeV, way less than a second. And this is the oscillation is for the million years. So you can imagine it's just pushed away or driven by the oscillation of axion. During the process, also, we have to admit this introduced inevitably a subcomponent of dark matter. So this, well, because we all know that the axionic or the scalar from this alignment is going to behave like a cold dark matter. So if we want to describe the fraction by this dimensionless x, well, I mean, just the axion dark matter fraction over all matter. From this point of view, like say, if we put an M plot right here, the Merkel field tells us this can be order 1%, but this is typically allowed. Well, though it's ultralight dark matter, but we find it's not only allowed, it's actually favored. So the reason is that we need to go back to the point. When we introduce the early recommendation solution to Hubble tension, we come to the dilemma that we need to introduce more cold dark matter. Remember? So we need to do this to fit the CMB and also BAO. This means more matter, and the more matter brings you more structure formation, or like say the growth of structure, and therefore higher sigma 8. As shown by this plot, that these models like successfully alleviate Hubble tension by early recombination, but inevitably hit the higher S8. But this is not a problem for our model because we have the axion that's like say it's quantum pressure and the potential force together for suppress the structure formation below the gene scale that's shown right here. This is like say there's no axion, like say this how the matter power spectrum look like. This is well the relative value. And we are not going to chop off the matter power spectrum solely, but by introducing 1 to 2% of the axions, we see that, like say, the suppression is good enough to bring this back to the preferred regime, and it fits the theoretical calculation pretty well. So at the end of the day, we just put a more realistic analysis and see that the constraint with a non-zero axionic dark matter. This is like the overall, like say in the SA Hubble plane that's like likely to be problematic, and we see we perform way better than lambda CDM. We also compare with the original model that only the VEV is changing, or effectively only the electron mass is changing, and we still perform much better in this preferred regime. So now let's switch gears. So we kind of like ended the discussion about the CMB related observables. It's important, and another important piece is the BBN, which is also significant. At the very beginning, it may seem a little bit like too easy, but still, you can see there are many parameters that comes in, say the time or the temperature of the neutron-proton conversion ends, while the neutron lifetime, and also the neutron formation time. Well, I mean, so on. So these are, like you can see, this is the electroweak process. So the W mass, the up and down quark mass, and the difference, and also the lateral mass is going to change, and that they all change with the back. So you can see the Fermi constant is going to change. The only electroweak interaction that matters is the NP conversion or neutron decay. So as the electron mass, and so as the isospin breaking effect. But in order to make lithium, just like as this ultra simplified picture, but still complicated, you need to go through many nuclear interactions in order to bring beryllium-7, and at the end of the day, they just decay to lithium-7 after the BBN. So here comes the most important or most interesting thing, the quark mass on average, that also changes the VEV. And this involves like a strong nuclear interactions, and no problem, like say, because it's at the end of a very complicated chain, we expect significant changes. And indeed, from a very simple point of view, we can know this from the just like a toy chiral perforation theory, that if we increase quark mass, then the pion mass must increase. And as predicted by Yukawa like a century ago, that this makes the nuclear force connecting nucleons, like say binding neutrons and protons together, is more short-range force. And therefore, heavy nuclei that relies more on these binding energy suffers more. They become more fragile. As indicated here, you can see that these heavy guys, beryllium-7 and the lithium-7, becomes more fragile, more sensitive to the quark mass difference than, well, I mean, the lighter counterparts. You can also see this from this, law of dependence of parameters, and all these electroweak inputs. Well, the effects rather mild, I would say, but the quark mass, you can see the suppression of lithium abundance. Well, I mean, you have, easy physical explanations. So we put, like say, we have just a small fit using PBN data only, and we find this region that basically lives with everything within like 2 sigma or so. And we find out that the preferred delta V we have is actually around 1%, just solely from PBN. We don't know anything about CFB, but this is good, right? And we also find that the baryon fraction increased by 1 to 3%, but this also overlaps with our CFB preferred preference region. So there are other pieces, so I mean, just talk about them briefly. This is like ICP, bright regions. The idea is very simple. So you just have this coupling, very natural. You have an axion, you have this coupling. If you parameterize this way, and as the axion fields kind of change from the very beginning, a high value to nowadays 0, then the difference kind of introduce, coupled to this E dot B in electrodynamics, and start to rotate the plane of CMB photon polarization, and eventually gives you this parity odd component. And this beta angle of this like rotation is described by this equation. Very simple. So what we are interested, because this is nowadays it's effectively 0, so we're interested in what's the initial value of this. And in the preferred mass regime, say 10 to the minus 29 eV, it's rather mass insensitive, maybe from the previous paper. So from the observation that nowadays this 2.4 sigma non-zero beta angle, we immediately get that the initial value of A over FA is a natural number, which is the 1, right? So no need to fine tune, like say 2p pi or like say 10 to the whatever angle. So at last, you may be worried or curious about this is a living thing, right? So the axion field is still alive and around changing physics. So what possibly we can do to detect from, like, say, different experiments or observations? So far, the strongest constraints coming from the atomic clock measurements. So because it's still changing, so we expect that the effective electron mass here, the electron proton mass ratio anyway, is still have an annual drift. And from this 10-year span of Ybberian atomic clock, we find out that the best constraint is like order 10 to the minus 6 inverse year. This immediately puts that constraint on axion mass to be greater than 2 times 10 to the minus 30 eV. Lighter ones means that the damping or the oscillation is too strong nowadays. It's not going to survive. But still, our preferred regime is actually, like, say, 1 to 3 times 10 to the minus 29 eV. That's more ideal for us. And in order to make fundamental discovery or exclude everything, we need to go, like, say, 2 orders of magnitude further, down to 10 to the minus 18 inverse year position. But this is foreseeable within 1 to 2 decades, given the fast progress in the field of atomic clocks or even nuclear clocks that evaluate directly, not only measuring electron mass, but also the quark mass. Alternatively, we can also go to the distant past where the fluctuation is still, more vivid, say in the high Z, so-called high Z regime. We point the telescope there, and we hope, or like say, indeed, the molecular spectra, the richness, like say, different modes, they have different dependencies on delta V that kind of disentangle the uncertainty of the redshifts and also delta V. But so far, you can see that the measurement, the quality of the measurement is not enough to even, veto the 1 times 10 to the minus 30 EeV solution. So we may wait for longer years to see if it's doable. So here comes our summary. So this is just basically for different benchmark masses. We still don't know which one is the best, and the different parameters summarized. And here shows that previously these 4 pieces are discrepancies, but now they serve as evidence that they coexist and they live together right here. So which is a nice sign. So as a take-home message, I would just just review on the whole idea again that the higher Higgs VEV when or before the recombination is preferable because it brings you early recombination. Is the standard recipe one of the preferred way to solve the Hubble tension. It's compatible with the BBN data, and also it somehow just solves the lithium-centered problem. Beyond that, by going an axionic solution using the axion rather than anything else, it's going to alleviate the tension of sigma 8, because this previously would make the early recombination solution less preferable, but now it's just okay. It's part of the. Naturally comes out with our choice of data. Parameters. It naturally explains if there's non-zero ICB almost for free, and it grounds its accessibility to directly observe this field and to confirm and separate from other models. Thank you.